that's our introduction done with. What we're going to do now is dive into some network fundamentals. Now, most people in their day job, and I'm guessing this is true of most people in this room, you have to be a jack of all trades, right? When you work in a school, you have to know how to do basic networking. You have to know how to do MDM and provision applications on devices. You have to know how to image machines and all of that stuff. There are some people who has a day job like myself, and all I do is networking. And so I acknowledge that when you're a jack of all trades, you have to know as much as you can about all topics. But sometimes you kind of misdefine the details because honestly, you don't have to do that in your day job and things just work. So what I'd like to do now, hopefully, is give you some information that you might not know and explain a little bit about how networking works at the base level. So we're going to start at layer 2, and then we're going to work our way up to layer 3. And so when we talk about networking layers, we're using the OSI model, and we have layer 1, which is the physical hardware. That's the cable. We have layer 2, and we're going to talk about that. Then we'll talk about layer 3. So if we have a network such as this, we might have a switch with a few devices plugged into it, right? Pretty straightforward stuff. We've got 2 hosts. We've got a router that gets us out to the internet, and these devices are plugged into a switch. So we have a thing called a MAC address. Theoretically, every Ethernet device on a network has a unique MAC address, which is assigned only to that device. If we had 2 devices on a network with the same MAC address, MAC learning on the switch would break, and communication wouldn't work well at all and would have lots of problems. In a moment, we'll talk about MAC address randomization, but for all intents and purposes, let's just pretend that every device on a network has a dedicated MAC address which is burnt into the device that can't be changed. A MAC address looks like this. So it's a hexadecimal value made up of, what do we have, say 6 octets. The first chunk of a MAC address is known as the OUI, which is the Organization Unique Identifier. And this is basically the manufacturer of the hardware. So if you look at a ruckus access point, if you purchase a couple of ruckus access points at the same time, and you may have seen this, all of your ruckus access points will start with roughly the same MAC address. And the reason for this is the OUI portion. It tells us that this product was made by Ruckus. It's the same with laptops. If you've got an HP laptop and you buy a bunch of laptops at the same time, they will all have the same first part in their MAC address. There's actually a website. If you go to Google and you type MAC address OUI search, you can go to a website and it will allow you to enter these first 3 octets, and you can actually search for which vendor made this product. Super useful, right? If you're trying to identify a device on a network and you have its MAC address, which is pretty common, you can just Google up this MAC address searching tool, type this in, and it will tell you what kind of a device it is. So you might know, like if it comes up and says it was made by Apple, it could be an Apple TV, could be a Mac, could be whatever, but it does help you sort of narrow down your troubleshooting. The second part of the MAC address is quite random. And the idea is that when a vendor makes a product, so at the factory, we have a factory that churns out access points. We have a process in manufacturing that basically increments the MAC address by 1 for every device that we manufacture. And when we run out, we'll go to a new OUI. So vendors have more than one OUI. And so that's how the MAC address works. Pretty straightforward stuff. So every device on our network has a MAC address. And here's an example. This is a very poor example because I've just, you can see what I've done. But yeah, just for argument's sake, say that that's how that works. There's one more MAC address which we need to know about, and that's a special MAC address, which is the broadcast MAC address. The broadcast MAC address means that if somebody sends a piece of information to this MAC address, that tells the switching fabric and the network to broadcast that packet of data everywhere on the network. So I'll give you an example in a second. So when a piece of information travels across a layer 2 network, it has a source MAC address and a destination MAC address. So if this host here, O1, wants to send a piece of information to this host here, his packet as it transits across the network will have a source MAC address and a destination MAC address. And the switch is aware, right? The switch's job is to allow traffic to flow or switch traffic between different ports. And so the switch has a process for MAC address learning. So the switch will learn that if a packet of information is destined for this host, that it should go out that port. And so MAC address learning is a function of the switch. at the top here, I have a screenshot of a Wireshark capture. And what we have here is the ARP protocol. So ARP, or the Address Resolution Protocol, is how we translate a MAC address to an IP address. So you guys will all know that you can configure an IP address on a piece of networking equipment, right? You go into the settings of your laptop and you can change your IP address. You can't change your MAC address though, right? I mean, it's pretty hard. You can, but technically you can't. The ARP protocol, or the Address Resolution Protocol, is how devices on a network translate a MAC address to an IP address. And the way that it works is we do a broadcast. So do you remember how I said if we send a message to FFFF, it will go everywhere? And so what happens is the very first time this host here wants to communicate with this host here, he will send out a broadcast ARP request on the network. And he'll say, I want to talk to the IP address 1.5. I'm sorry, that should be 1.2. My diagram's all mixed up, but you get the idea. But he'll say, who has 192.168.1.5? And this message floods out the network and it goes everywhere. It goes to every host on our VLAN or our layer 2 network. And we'll talk about VLANing shortly, but this feeds into it. And so the more hosts you have on your network, the more ARP traffic you're going to have flooding around, right? Because this learning process takes place. And then hopefully what will happen is somebody who actually has that IP address will reply. So this guy replies, he goes, oh, I have 192.168.1.5. And then he sends a message direct back to that host. Says, I have that address, and by the way, my MAC address is this. So if you want to talk to 192.168.1.5, you should direct your layer 2 traffic to this MAC address. Bear with me. If you're on a PC or a Mac right now, you can pop open your command line, and you can run this command, ARP-A, and that will show you your ARP cache. If you're on a network, whether it be a Wi-Fi network or a wired network, go ARP-A and it will show you your ARP cache. So ARP cache looks like this, right? So this device has learned that 192.168.1.1 is at this MAC address, and 192.168.1.2 is at this MAC address. And so that if I already have an entry for a device in my ARP cache, I'm not going to go through the Address Resolution Protocol every time I want to talk to the device. I already know the MAC address of the device, so I can communicate directly to it. But if I don't have the MAC address of the device in my ARP cache, then I'll go through the Address Resolution Protocol and send out a broadcast and work out who has it. Cool. Everyone with me on that? So that's ARP Layer 2 communication. All right. So the next thing is, you'll notice in my diagram I also have a router. The general rule here, I think I have a slide that tells us about this. Actually, we're going to come back to this in a second. Now we're going to move on to VLANs. So VLANs are a tool we can use to segregate a switch into different logical networks. VLAN is a layer 2 network, meaning if I send out a broadcast, if I send out an ARP request, that ARP request will go to everything on my VLAN, everything on my layer 2 network. So on a ruckus switch, you can set up VLANs by just running a couple of commands. So here's an example. All we do on the switch is we would type VLAN 5. This would create VLAN 5. And then we say untagged Ethernet port 111 to 118. We'll talk about port assignments later, but what we're saying is that port 1 through to port 8 are a member of VLAN 5. Very easy. And we also have VLAN 6. And we're saying port 9 through 16 are members of VLAN 6. If we create these VLANs on the switch, this means that a host on VLAN 6 cannot communicate to a host on VLAN 5 at layer 2 because these are separated networks, separate logical networks. And so in order to keep our broadcast traffic down, one of the techniques we use for this is we create VLANs. If the internet was all one VLAN or one big network, it would completely be broken, because imagine if every device on the planet was sending out an ARP request onto a network, it would just be completely overloaded. And this is one of the reasons why we have different network segments. In this example, I'm showing here that our VLAN 6 network segment also has a router. If I want to communicate to a device that's outside of my VLAN, what happens is your host will forward the traffic to its default gateway, which will be the router. The router then has a link into another network upstream and is responsible for forwarding that traffic outside of our subnet. So this diagram I've drawn here is something that doesn't normally happen in reality. I've drawn a router for each of my VLANs. And this absolutely is a supported configuration, and some people do this. But it doesn't make sense to have to buy 2 routers. So what a lot of people do is they just use a single router. So I could have a single router. Now, how do we deal with this? What we do is we have a special port on the switch, which is configured as a tagged port or a VLAN trunk port. If you're coming from Cisco terminology, they call it a VLAN trunk port. We call it a tagged port. So in our configuration, where previously we had VLAN 5 and VLAN 6, we had the untagged ports, which was from 1 through 8 and from 9 through 16. I've added an additional line here to say tag on port 121. So by the way, this is port 121. We'll talk about port assignment later. So what we're doing is we're taking VLAN 5 and VLAN 6, and we're transporting both VLANs down that single port. Now, let's just take a closer look at how that works. So this is a packet capture from a piece of software called Wireshark, which shows us traffic as it's floating around the network. Remember how we were talking about layer 1, layer 2, and layer 3? This basically is layer 1, layer 2, and layer 3. Right? So layer 2 is MAC address based, layer 3 is IP address based, and then we get into application layer, like layer 4 and beyond. And so in this packet capture, we can see that there is a VLAN tag or a VLAN header frame, piece of information that has been added into the frame. Now this line here tells us that the VLAN for this packet of data as it transits across the network is VLAN 1. But this could be a number from 1 through to 4095. So we could have 4095 VLANs on a switch or a single network. And believe me, like I am aware of customers who have exceeded that number of VLANs. We have customers overseas where they have like universities and they have student accommodation, like dorm rooms, and they have each dorm room on its own VLAN to segregate the traffic. So there are situations where you could do more than that, but there's other technology we use to get around that limitation. But I'm not aware of any school in New Zealand that's using more than 4,000 VLANs. Okay, so that's the VLAN tag. So the VLAN tag was put there by the switch. By running this command here to say tag Ethernet 121, that instructs the switch to add that piece of information to the packet header. So that was put there by the switch, or it was put there by the firewall. So in this case, both the firewall and the switch are VLAN aware, and they're adding the additional piece of information to the packet header. All right, let's build our network up a little further and get a little bit more complicated. And so we've obviously got our switch talking to a bunch of hosts with different VLANs. A VLAN trunk port or a tagged port also can transit our networks to other devices. So if we have another switch on our network, we're going to use the tagged port between these two switches to transit the multiple VLANs. If we have a Ruckus access point plugged into that switch with different Wi-Fi networks, one for staff, one for students, we're going to use a tagged port to transit those two VLANs to the access point. I think these are most of the scenarios I can think of. There are other scenarios, like if you've got a VoIP phone, sometimes that would use a different VLAN and also does VLAN tagging. But yeah, there are some other scenarios, but this is a kind of basic config, right? So we're tagging on 121, which is going to the router, and we're also now tagging on 134, which is going to the other switch. Any questions around that?
Do you have to use the tag port to go between switches, or are you only doing it when there's multiple VLANs?
Great question. You don't have to use a tagged port to go between switches. If you've only got a single VLAN that you need to transit, then it wouldn't be a tagged port. You can just use a regular port to go between switches.
If you essentially stack two switches together, do you have to configure them manually and just tag your VLANs to the trunk?
Great question.
Or is it one thing where you say, I want this to be my stacking port, and it just tags every VLAN?
Yeah, great question. Yeah, so the question is, if you're stacking switches together, do you have to configure the port that goes between your switches for different VLAN tags? And the answer is no. The port that is used for stacking ruckus switches together is a dedicated special stacking port, and you put special configuration on that port to say, hey, this is a stacking port. And by default, all VLANs will transit down stacking ports.
So stacking ports are like automagic, but if you were to use like different vendor hardwares, then you'd probably want to do VLAN tags, depending.
So as soon as you tag it as a stacking port, it automatically tags
Yep.
one through 4952.
Yeah.
Exactly.
Or we could just untag it.
Yep, perfect. All right, let's move on to the next subject here. Going to be a bit rude. There's an acronym that we use. It's called BUM. Broadcast, unicast, and multicast. And there are 3 types of traffic that can transit across a layer 3 network. So the first is unicast, which, as the name suggests, goes from one host to another. So we have a source IP address and a destination IP address. Pretty straightforward stuff. The next one is a bit more complicated, and that's multicast. The idea behind multicast is if I have one transmitter and multiple receivers, but not everyone is going to be receiving this traffic. Let me give you an example. When I was working in schools, we used a piece of software called Semantic Ghost to image all of the machines in the computer lab. And the way that that worked is it could use multicast technology. So the server would transmit one piece of information that would be received by the 30 computers in the classroom. They would acknowledge that, and then the server would transmit the next piece of information. And so that's multicast. So the packet was going only to the machines who had subscribed to that multicast group. Another use case for multicast is video or TV technology. In hotels, they have IPTV systems. So what they have is this device sitting in the back office, which is an IP encoder. And they take the TV signal from the antenna, goes into an encoder, and that encoder plugs into the network, and it transmits on a special IP address, and anybody who subscribes to that IP address will begin to receive the signal for that TV channel. And so this is multicast. One of the things about multicast is you can see here our destination IP address. There is a special IP address range which is used for multicast. If you see an IP address that begins with 239.1, this tells us that this is a special multicast packet. All right, then we have broadcast. So broadcast is always the last IP address in the subnet. So I don't know about you guys, but at home, I think I use 192.168.1.1 on my router and my network. The last IP address available within that subnet is 255. 255 is the broadcast address. So fun fact, if you go to your computer and you ping the broadcast address, you will actually send a ping out to every device on your local layer 2 subnet. And then you get all the devices reply, and it's quite cool. You get multiple replies coming in from all different devices. So it's pretty neat. But a broadcast request is so broadcast is used for ARP resolution. Broadcast is used for a bunch of other stuff as well. But if we have too much broadcast floating around our network, it does become a problem because there's just too much traffic to process, because broadcast requests go to everybody. Unicast requests only go out the switch port, which they're destined to for that individual host. But broadcast requests are forwarded by the switch out to every port. Any questions on that? I would say most traffic on a network is going to be unicast. So from a host directly to a web server or to a service. That's all unicast traffic. All right, so there are 2 types of IP addressing in use in the world. There's IPv4, which was invented 2 years before I was born, and there's IPv6, which is the more modern standard. So, put your hand up if you're someone that uses IPv6. Wow, 1, yep. Most times, there is no one. And so, let me explain. So, IPv4 is an IP address, which is a 32-bit address, which is made up of 4 octets, and we're going to go into that in a moment. But because of that, there are only 4.3 billion unique IP addresses in the world. This means that given all the devices we have in the world, there are not enough IP addresses for each device to have an individual unique IP address. And this is why on a private network, we have private IP address ranges that go through a NAT router that gives us internet access. And we're going to get into IPv4 in a moment. IPv6 is the world's answer to fix this problem of only having 4.3 billion IP addresses. There are 340 trillion IP addresses available in IPv6. The problem is, this is an IPv6 address. I don't know about you guys, but I can remember 192.168.1.1. I can remember that in my head. If I'm configuring a printer from a printer panel or something like that, it's pretty easy. I can remember that stuff. But there's no way I can remember this in my head. And in my opinion, this is the reason why IPv6 has not been widely adopted. Because it's just not easy for humans to read and then memorize. Yeah, but IPv6 will be the future. Like one day, IPv4 will be phased out. It might be 20 or 30 years from now, but it's going to happen at some point. So while we're talking about IPv4, let's talk about the different IP address ranges that are out there and in use. So you will probably be quite familiar with the private IP addressing ranges. I guarantee you on your networks that you maintain, you're either using a 10 dot something or a 172.16 or a 192.168. These here are all IP addresses which are not routable over the internet. Theoretically, if an internet service provider receives an IP address receives a piece of information from one of these addresses, it should block that IP address. And these addresses are only to be used on private networks. Generally speaking, which one of these sort of spaces should you use? It's completely up to you. Like I know a lot of schools who use 192.168, and I also know people that use the 10 subnet. I guess the 172 I think is a little less common. I always tend to use the 10 subnet when I'm doing a network. And the reason for that is it offers the highest number of IP addresses. But with the 10 subnet, it's a /8, meaning that if I'm designing an enterprise network, what I would normally do is I would start with 10. I would make my second octet maybe the site, right? So if I had a branch in Wellington and Auckland, I would say anything in Auckland is a 1, anything in Wellington is a 2, right? So 10.1 means it's in Auckland, 10.2 means it's in Wellington. The third octet I would use to identify the service. So if I had multiple VLANs on a site, like one for students, one for staff, one for printers or whatever, I would use the third octet for my service. So like 10.1.2 would be the Auckland workstation VLAN. That's just how I would do it. You can do whatever you want. Let's move on. So we also have some other IP address ranges which are reserved and not considered to be public addresses. So because the world is running out of IP addresses, some service providers, maybe such as Skinny or someone like that, more of the budget service providers, do not give their customers a real world public IP address. So having a public IP address on your internet connection means that you can do port forwards and people can contact you. But what they do at some budget internet service providers is because they don't have enough public IP addresses, they will put you behind a NAT router, which means that you get a 100.64 address. This is a special address range which has been reserved for what they call CG or carrier grade NAT. And so if you have a 10.64 address at home and you're attempting to do a port forward from your router to a network device in your network and you're trying to get to that from the internet, it won't work because you're behind CG NAT. The other range is 172.0. And I used to have a t-shirt that said there's no place like 172.0.0.1. So it's a loopback address, right? It's like there's no place like home. It's like goes back to yourself. It's used for testing. There's the 169.254. If you've ever plugged a device into a network and that network doesn't have a DHCP server, you'll end up with an address in this space, 169.254. It's the automatic configuration address. Not many people use that for real. And then we've got the 224, which is multicast, which we've spoken about already. So look, there are a couple of other IP address ranges which are reserved for various things, but generally speaking, anything outside of this block of IP address ranges will be a public IP address, which will be on the internet, which is publicly routable. Cool. Any questions about IP addressing? Any comments? Excellent. let's dive into IP addresses real quick. So let's talk about IPv4. IPv4 is an address which is made up of 4 octets, and each octet is 8 bits big. So you guys know I didn't really finish school, so I suck at maths. But I had to learn how to convert binary to decimal. And so what we have here is 8 bits. And each of these 8 bits has a value. And so this is 8-bit binary. So it goes from 1 up to 128. The way that this works is using these numbers, I can make up to a maximum of 255. So I can actually make any number between 0 and 255 by using these bits. And all I have to do is tell the computer if I turn the bit on or off. And so if I look at 192, to get to 192, it's 128 plus 64. So that means that bits number 1 and 2 are enabled. And so this is 8-bit binary. You guys are probably smarter than me, you probably know more about it, but that's generally speaking how it works. Now when we configure an IP address in a device, we typically have 3 fields. We've got the device's IP address, we've got the subnet mask, and then we've got the default gateway. So here's the rule. All traffic destined outside our subnet is directed to the default gateway. And we talked before about the VLAN and the MAC address stuff. So anything that, if I have a 192.168.100, because my subnet mask is this, it means that if I have a piece of information which is destined for an IP address outside the 192.168.100 range, then it will go to the router. So the router can forward that outside my local subnet.
But if you don't have a default gateway, you can still talk to the clients on that LAN.
Yeah, good point. So fun fact, did you know you don't actually have to enter a default gateway when you're doing your network settings? If you don't put a default gateway, you can still talk to stuff on your layer 2 network. Okay, so here's an example of a packet sent inside the subnet. So if this host here, 100.5, wants to communicate to this host here, 100.3, how will this work? So the source MAC address is going to be the MAC address of this host. The source IP address is 100.5. The destination MAC address will be the MAC address of this device. And the destination IP address will be the IP address of this device. Pretty straightforward. Now, if I wanted to get to a different host, such as 8.8.8, because I wanted to use Google's DNS server, the MAC address source would be the same. It would be my host. The IP address source would be the same. But in this case, the device has recognized that the IP address I want to get to is outside of my subnet. So what it will do is it will forward this packet to the MAC address of the default gateway. And then the default gateway or the router is responsible for sending that packet up into the internet or to its next hop. Cool. So let's talk about subnetting. Pretty common, right? If I have an IP address like 192.168.100. whatever, my subnet mask might be 255.255.255.0. That's known as a /24. Why is it known as a /24? What does that even mean? It means there are 24 bits. So when I take the subnet mask and I look at the binary translation for each of these, they're all 255s, which means all the bits are enabled. There's 24 bits here, 8 plus 8 plus 8. So known as a /24. Pretty straightforward stuff. So in this case, my network, 192.168.100, so the network address is .0, which is not really usable. The broadcast address is 255 because it's the upper address in the range. And the valid hosts that I could have within my network would be 1 through to 254. And so this is my IP subnet, which is a /24. Now, the gateway IP address is 100% defined by the administrator. I can take a firewall, like a 40-gate firewall. I could slap an IP address on it, and it could be any IP address within that subnet, and that would be my default gateway. I could make it .100 if I want. I could make my gateway 192.168.100.100, so long as I program all my devices default gateway with .100. Excellent. Any questions about that stuff? Okay, so if I had a subnet mask that looks like this, I change the 0 to a 128. What does that do? That enables and makes this a /25 because it gives me one more bit. So remember our binary? The first bit here is 128. So what that's going to do is it's going to turn on that bit, which gives me a /25. What does that mean? It means my valid hosts within my subnet have just cut in half. And so my valid hosts now is effectively from, so my network address is .0, the first usable address is .1, the last usable address is 126, and my broadcast address is 127. And it's all because I've changed the subnet mask. So if a host in this subnet wants to communicate to 192.168.100.200, it's outside my subnet because this subnet now ends at 127. So because it's outside my subnet, it has to go to the router, and then the router has to send it there. Some more examples. So that's the one we did originally. A /30 is interesting. So if you have a subnet mask which ends in 252, this means that we have 30 bits enabled. People typically use a /30 for a point-to-point link. If you're an internet service provider and you want to have an IP address on the internet service provider's router and an IP address on the customer's router, you would typically use a /30 because there are 2 usable IP addresses on the /30. So it means we're not wasting IP addresses and we can cut it up. So that's an example of a /30. The other thing to think about is here's a /20. So in this case, the third octet is 240. This means that in this subnet, there are 4,094 usable IP addresses that we can have for hosts. So this leads me to my next question. In your schools that you guys look after, do you use a /24? Do you use a /20? I'm aware, I did this the other week, and there was a school that was using a /8. Their entire network was 10.0.0.0. Their subnet mask was 255.0.0.0. And so they had one big flat network, not very efficient use of the IP addressing we had available. So on one hand, you want to have a lot of IP addresses available so you can get lots of devices on your subnet. On the other hand, if we have a lot of devices on our subnet, we could have more broadcast traffic floating around, which makes the network more inefficient. And so a bit later this afternoon, we'll talk about how the N4L secure access program does subnetting. But yeah, I mean, it's a trade-off. Some schools do a VLAN for every year level of students. So you might have like, a few hundred students in each VLAN. Some schools do one VLAN for all of the students. It all depends on the size of the school, how many students are in each year level, and other factors like that. But we'll have a chat about that a bit later on. Cool. Almost finished. So in summary, IP addressing. So without subnets, the whole world would be one big broadcast domain and it just wouldn't work because there'd be too much broadcast going around. Breaking up different layer 2 networks also allows us to implement different firewall rules for each VLAN. So if we had a VLAN for staff and a VLAN for students, we can tell our firewall that any piece of information coming from the student VLAN has a specific content filtering policy before it goes out. So another reason to break your network up into different subnets is if you want to have different firewall rules and filtering as to where that network can access. So subnets should be broken up by service, or as they're routed by the firewall. And this allows us to have different policies that are applied to each subnet. So if I have a subnet, especially for my printers, there's no way, well, mostly speaking, there's no way that a printer really needs to access the internet. Some of them do automatic updates or whatever, but generally speaking, if a printing device tried to get out to the internet, that could indicate to me that there was a security problem on my network because these devices shouldn't be going out. And so that's an example, right? You can block internet access for certain networks or whatever. Okay, so let's move on to something a bit lighter. Power over Ethernet. So this is a bit easier. So things you should know about power over Ethernet. PoE has many standards. So the most common standard, 802.3 AF and 802.3 AT. So just a side note, the AT has nothing to do with allotalysis, it's just the name of the standard. So standards-based PoE is based on a range from 48 to 56 volts. The reason it's a range is because if I start transmitting 56 volts at the source, by the time it gets down 100 meter Cat5, Cat6 cable, it's probably not going to be 56 when it gets to the other end, right? But it should be above 48 when it gets to the other end. So it's based on 48 to 56, and this is designed to go over a standard Cat cable, whether it be, even Cat5 all the way up to Cat7 now. So there is, however, lots of networking equipment floating around the market that's not standards compliant. And so just be aware of this. I hate naming other vendors, but this is the only one I could find. And so this is a product made by a company called Ubiquiti. Their access points, or some of their access points, not all of them, some of them do 48 volt, but this particular product is a 24 volt PoE system. And so if you were to plug their access point into a 48 volt system, you run the risk of damaging the product. And so generally speaking, most vendors in the industry conform to standards-based PoE using 802.3 AF and AT. But just be aware that there are a couple of vendors out there, and they're normally on the cheaper side, that don't conform to the standard.
With your 4856, over, say, standard Cat6 network, so that's probably what most of us have, what's the sort of range that you're looking at over moderately decent cable?
So it's 100 meters. It's designed to work over, 100 meters is the golden number for a Cat cable. Yep. So you can pretty much guarantee that over 100 meters, it'll always work. All right, so let's look at how the PoE is actually transmitted down the cable. These days, most network devices are 1 gigabit devices. However, before that, we had 10100 devices. And so the 10100 devices actually had the option of pushing the PoE down the spare pairs. So a 100 meg connection actually only requires 2 cable pairs. So you've got transmit and receive, and that will get you a 100 megabit connection. When I was working in schools, we had this adapter. It was like a Y adapter. You plug it into a single Ethernet outlet, and it'll give you 2 ports. So that only works on 100 megabit though, because what it does is it takes 2 of those cable pairs for transmit receive and splits it off there, and get the other 2 pairs there. The bit I missed is that a Cat cable has 4 cable pairs with a total of 8 conductors. And so, originally for 100 meg, what we did was we put the power down the 2 pairs which were not being used. And then they invented gigabit. And then we had to come up with a solution. How do we, all 4 pairs actually get consumed with gigabit networking? And so there's actually 2 different modes in which we can operate PoE. There's a mode A and a mode B. So mode A is probably the most common these days. This is an example on 100 meg, but it's the same on gig. Mode A mixes the data and the power down the same cable pair. What it does is it takes the data signal and it increases the voltage of the data signal, like up to 48. And then what it does is the device on the other end receives that, takes the 48 it needs, and then passes the data signal on to the rest of the electronics. And so that's the most common mode. But there are still some scenarios where people do use mode B, which is where you use the spare cable pairs. So yeah, keep that in mind. So we spoke about the voltage, but what we didn't talk about was the amount of power that devices consume. So when we talk about power, we're probably talking about how many watts does a device consume. And so there are different standards to define the maximum amount of power output on a PoE device. And so the most basic standard is 15 watts. That's 802.3 AF. Then we also have PoE Plus, which is a 30 watt standard, and this is most common now. Going all the way up to 802.3 BT, which can deliver up to 90 watts of power. I think at that point, if you're only using an old Cat5 cable, it might be a bit warm, that cable. But if you're using a Cat6 cable, you'll probably be okay. And so the idea behind that, why would you want 90 watts of power delivered over PoE? You can now get display screens, digital signage screens, which are powered off the Ethernet cable. So if you're putting a digital sign somewhere in your school, all you got to do now is run a single Cat cable, and you don't have to run a mains power outlet to that location, which is kind of handy. The other thing is Philips have an in-building lighting system which works off PoE. So imagine that, you reboot. It's not the Hue, no, it's something else. The Hue is the Zigbee thing, but yeah, I forget what the product range is. But yeah, think about this, you reboot your PoE switch and all the lights go out. But we have actually a solution for that. So some Ruckus switches have a feature we call perpetual PoE. So you reboot the switch and it keeps the PoE power on, even when the software is not active on the switch, which is quite cool. Yeah, so that's PoE. Look, so we should probably talk about this in the context of Ruckus equipment. And so in the context of Ruckus switches, what I can tell you is that the 7150 switch, which has been deployed as part of the ministry's network hardware replacement program, the 7150 24-port switch provides us 370 watt PoE budget. So if we take 370 watt and divide that by 24 ports, that'll get us 15 watts on every port. But if we have a 30 watt device, then we can supply 12 devices at 30 watts on this switch.
Can you say bench between 50 and 30?
Yeah, absolutely, absolutely. So you could have some 15 watt devices, some 30, and it's dynamically allocated. Yeah. And it's not a specific port, right? So all 24 ports on that switch are PoE ports, and then it automatically negotiates how much power is required and allocates that power to that port. And we'll look at that in a moment. So as part of the hardware upgrade program, there's also a 48 port switch, the 48P. This also delivers 370 watts of PoE budget. So on the 48 port switch, you can have 12 devices at 30 watts. So by the way, the Ruckus access points that are being deployed are 30 watt devices. You can get these to run at 15 watts, and we'll talk about that a bit later. There is also a model which is the 48PF. Now you notice that, so the P means power. We have a 24 without the P, which is not a PoE switch. And then we have the F. The F means full power. And so the PF doubles your PoE budget from 370 to 740. So at this level, we're able to output 48 ports at 15 watts or 24 ports at 30 watts. And then we also have, look, that 8-port switch is going end of sale, so we're not doing that anymore. But we have the 12-port switch, which is 124 watts, which is the guy we have here today. Excellent. So if we dive a little bit deeper, apologies if you can't see this, but this is an output from a PoE switch. And what we've done on this switch is we've done the show inline power command, and it tells us here that this switch, let me see if I can read this correctly, this switch has 1400 watts of PoE available. It's one of our other products. And so that's the total that the switch has available, and this is how much is currently free. And what we have is we go down, these are the ports on the switch, and port 1 has currently been allocated a 60 watt device. And here we have port 5, which has a 4 watt device. And so the power allocation occurs automatically based on the device that plugs into the switch and negotiates how much it needs. So the device has some electronics in it that tell the switch how many watts or which class of power this device is. Now I don't have a slide that details all the different power classes, but you can do some Wikipediaing and you can see that there's power class 1 through 8. Actually, did I go through that slide already? Let's have a quick look. No, I don't think I have it. So there's power classes 1 through 8. And so basically power class 1 is 4 watts going up to power class 3, which is 15 watts. 30 watts is power class 4, and it goes all the way up to 90 watts. And so what you can do on a Ruckus switch is you can type this command. So I can go into an individual port, and I can say inline power, and then I can go power by class. So this is super interesting. A Ruckus access point, the R650 for example, is a 30 watt device, meaning that when you plug this AP into a switch, it will tell the switch, hey, I need 30 watts. The switch will then go allocate 30 watts of power to this device, meaning that no one else can consume that power. But the reality is the R650 access point really only consumes about 16 or 17 watts, or even less for most people. So this R650 access point has a number of other features. Let me see if I can show you real quick. without unplugging it maybe. So this is the 750, but sorry, I can't lift it up because it's plugged in. Let me see if I can deal with this. Hold on. All right, so on this access point, we've got the Ethernet port on the back, and it actually has 2 Ethernet ports. If I'm using the second Ethernet port on this access point, it will consume more power. This access point also has a USB port for future expansion. If I'm consuming a USB port device, it will require more power. You get the idea, right? There's a bunch of features on this access point that most people will probably never use. And so what we've had to do though, when we designed this product, because maybe one day someone might use that feature, we've had to specify that this is a 30-watt device, because one day it might draw more than 15.4. But in reality, this access point, if you're not using these features, will only draw like less than 15.4 and can operate at a class 3 level. So this is a dilemma we have, right? We have to tell everyone it's a 30-watt device, which means when you plug this into a switch, the switch is going to reserve 30 watts of power, meaning the total budget in your switch is actually reduced. There's a bunch of power that will never be used because that device is never going to get anywhere near 30 watts. So at Rakus, we're currently working on a software feature for our switches, which will allow oversubscription on the power. It kind of breaks the standard by doing oversubscription though. For the meantime, what you can do is you can run this command on a switch. Excuse me. If you run this command, you can force the switch to lock that port in at class 3, which is 15.4 watts. And this will allow you to power more access points from a single switch. So even though that switch has only got, say, 12 ports or at 30 watts, you could have 24 ports at 15 watts. So you can actually double the number of access points that you're powering by manually forcing that port to a 15-watt operation.
When you do that, is the access point or other device connected to the other end aware that it has a reduced limit?
It is, yeah. So the switch communicates to the device and goes, hey, I'm only giving you 15.4. In some cases, with our higher end access points, it will actually reduce the power output of the access point as well. So one of the other things that happens, if the access point detects, hey, I'm only plugged into 15 watts, then it will reduce its power output by as much as 3 or 6 dB. Excellent, that's PoE. Any questions on PoE before we move on?